Ladies and gentlemen, welcome to Engineering Dynamics. In this video, we will be talking about the Lagrange multipliers and how we can use them to actually see the reaction forces in our system. Let's jump right in. So the main goal of the Lagrange multipliers is to see the reaction forces in our equations of motion. As we know from the last videos, when we project our equations into the directions compatible with the constraints, we eliminate all reaction forces. But in engineering, it's very often useful to actually see the forces to know which forces are acting, and depending on that, to dimension your system in the right way so it doesn't break. So sometimes it is necessary to actually see the forces. So before we do the whole theory, we jump right into the example. So we had this double pendulum where we had an angle alpha here and an angle beta there. But now we want to see the forces that are in this segment. So to do that, we first of all have to know the direction of our force, and then we have to know the scalar multiplier. So this will be exactly our Lagrange multiplier. So if we know we have two parts to a vector, so a length and a direction. So we first of all have to know the direction, and then we have to know the length. And depending on that, we have, and when we have that, we have the force that is acting in this constraint. So we have, of course, two forces because action equals reaction, but they both have the same Lagrange multiplier because one force is equal to the other force just in a different direction. So both of them have the same length and but pointing in different directions. So what we do now, we go from our minimal set of degrees of freedom to a set of degrees of freedom that does not that is not the minimal set. So we had alpha and beta here because we have two bodies. And if we have two bodies, we have 2 times n degrees of freedom. So that's 4, but we have two constraints. That's constraint number 1, and that's constraint number 2. So 2 times 2 minus 2 is equal to. So 2 degrees of freedom, 2 degrees of freedom. But now we have a set that's not a minimal set of coordinates. So we have alpha, z, and x. So we specify the position of this mass in our global coordinate system. So we can get the position of our mass 1, that's here, mass 1, and this is our mass 2. And of course, we can derive it with time, so derivation once and derivation twice. And this is used for our Lagrange 2 formalism. So just like we had the last time, we have the kinetic energy of our system. First of all, we take mass 1. So mass 1 is, again, the kinetic energy is 1.5 times m times velocity squared. This is our velocity squared. And because I took the cosine and the sine, it's just basically a 1 if I multiply it with L here, multiply it with L here, here, and there. So we are left with 1.5 times m times L squared. If I do this with the second mass, right there, we have, again, mass is the same, 1.5 times the mass times the velocity of the second point. And the velocity of the second point is described by the change of position in x plus the change of position in y, and both times squared, of course. We do the same thing with the potential. So once we have the potential for mass 1 and mass 2, we then could apply our Lagrange formalism where we can get the equations of motion just by deriving the kinetic energy, the potential, and setting it equal to our applied forces, in which case we have none here, so it's 0, and then we have the equations of motion. But this only works if we have a minimal set of degrees of freedom, but right here we have x and y. So let's go back to here. where we need to, first of all, find the direction of our force that we're looking for. And now we come to the theory. So the first thing we have to do is to do a variation of our constraint. So we know that our constraint in this time is f. For example, let's choose a simple one. We have x squared plus y squared equals L squared. We have to set it to 0. So x squared plus y squared minus L squared is 0. This is our constraint. And now we have to vary it. So a variation, we first of all have to derive it by our duik's and multiply it with a delta uik. And because we know that our constraints are always 0, that's how we define them, we know that also the variation is 0. And now we see that this is the same thing that we had before, where we have basically a projection of this vector and this vector. So that's how we get the direction orthogonal to the virtual displacements. So this is our virtual displacements, where the particle could move to. And we know that this is a direction orthogonal to the virtual displacement. So this is our constrained direction. So that's how we get the direction where the reaction force is pointing to. If we look at an example, so here we have the direction, and here we have our virtual displacements. And if we do a sum, so the scalar product, this sum, we get 0. So this is something we just use to get, first of all, the direction. So now we can describe the reaction force. So we have a reaction force, and this is again the scalar multiplier and the direction of our reaction force. So here again, we have a intensity of our reaction force and the Lagrange multiplier. That is the Lagrange multiplier. If we look at an example right here, we have our constraint that we had beforehand. So this one, basically. And now if we do a variation, we get these two positions, or basically this vector, and our virtual displacements. The virtual displacements go along this direction, and the 2 and 2 goes into that direction. So we get the exact direction we want to have. So when we now look at the virtual work of our reaction forces, we know that if we project it, it will be 0, but right now we're not projecting it into the minimal set of degrees of freedom, and that's why they don't disappear. So we have the reaction force, or let's start right here. So we have the virtual work is our reaction force times the virtual displacements. Now we input our reaction force with this one that we had before and have again, multiplication with our virtual displacements. Now we change the virtual displacements. Sorry for that. Now we change the virtual displacements to virtual displacements only dependent on our q's. And now we can use this whole expression and input it into the principle of virtual work. So again, we have our m, we have our u double dots minus the forces, minus the reaction forces that we just described, and the projection. But here, this and that, this doesn't disappear because our q's, again, like the example beforehand, are not these minimal set of degrees of freedom. So we go from 1 to n, and from 1 to n, so these are the amount of our degrees of freedom, but not minimal degrees of freedom. So we have more equations. So let's jump right in. So we had, in the beginning here, we had two masses, two constraints. That means 2 degrees of freedom, which also means that we have 2 equations of motion. If we have 3, we have more. So this is, in this case, n, here is n equals 2, and here we have n equals 3. But because we have now more input, so first of all, we have 3 equations of motion, but we have, in this case, our unknowns are alpha, x, and y. but we also have this unknown variable of our scalar, so of our Lagrange multiplier. And this is something we also have to find out. And we can't do this only with this equation. That's why we have to add this constraint equation, so that we have four variables and 4 equations. So we have 3 equations here, 1 here, and we have 4 unknowns. In our case, we have alpha, x, y, and lambda. We know the direction, so that's what we don't have to find out. We have only to find out the intensity. Of course, the principle of virtual work is very tedious, and that's why we have to apply the same logic to our Lagrange formalism. So if we do it with Lagrange, we have the kinetic energy, we have the kinetic energy derived with our q dots times the time derivative and all the equations we had before. But here, sorry, this is wrong. Here we have our reaction forces. And again, we also have to add our constraint equation. If we look at an example, it will look like this. So we first have the first equation of motion. We have the derivation regarding alpha, alpha dot, alpha, and alpha again. Then we have here the x's and x dot, and here we have the y's. So our unknowns are lambda, x, and y, and alpha. So we have 4 unknowns, 3 equations, and that's why we have to consider the constraint of our last point that we are describing, not with a minimal set of degrees of freedom, but with more degrees of freedom. So I hope this topic or this video gave you a basic overview over the topic of the Lagrange multipliers. If you have any questions, you can put them in the comments down below and I will do my best to answer them. Please check out the other videos that I have where we actually do exercises, because just the theory is sometimes very difficult to understand that, and my videos maybe not be the best, but I'll hope that you got a general understanding. And again, if you have any questions, put them in the comments down below. Thank you very much for your attention and see you next time.